Hello everyone, Mr. Sutherland here with our final notes video of the school year. I appreciate your attention, your effort during this time. I know it has not been easy to learn this stuff on your own, but you guys really have done a nice job with it. What we're going to do today is we're going to look at normal distribution just a little more and normal distribution problems that require a calculator. So why would a normal distribution problem require a calculator? Well, if I look back at our notes from last time, all of these problems that we did with normal distribution, I would ask between 18 and 21 hours, which are numbers that were on our chart as either the mean or one standard deviation or two standard deviations away. And then we could use the empirical rule, the percentages that we knew, and answer the question. But what happens if I asked about 22 hours or 23 hours? What do we do then? So that is going to be our focus today. So let's look at our first problem. The light bulbs used to provide exterior lighting for large office buildings have an average lifetime of 1,000 hours. So there is our mean. The length of the life of the light bulb is normally distributed with a standard deviation of 50 hours. A light bulb is selected at random. Now, before I even have to go through the questions, I'm going to go ahead and draw our bell curve and label what we know. So 3 standard deviations above, 3 below. We have 1,000 here in the middle. So 1,050, 1,000, oh, that would be 1,100, and 1,150, and then 950, 900, 850. So the question is, what is the probability that a light bulb will last more than 10.75 hours? Or excuse me, 1,075 hours. Well, here's 1,075. So the question is, what is that percentage of the data? Well, we know at up to 150, it's 84%. So I have 16% of the data. Here it's 97.5%. So my answer is going to be somewhere between 2.5 and 16%. But how do we find that? So there are two ways. I'm going to show you about both ways. We're really just going to use one of them. Now, one way you could do this is through the z-score. And this is why one of the reasons we do use z-scores beyond comparing. This is really how it was done before the power of the normal distribution was really installed on the calculator. And what you would do is you would find the z-score. So the z-score, I would do 1,075 minus 1,000, so 75 over the standard deviation of 50. That means I get a z-score of 1.5. So this score is 1.5 standard deviations above the mean. Then in your textbook online, you would find a z-score table. And what a z-score table does is I would go to 1.5, and this is 1.50. So if I go where those intersect, that tells me the probability that it would be that value or less. And so since we're talking about greater than, we would do 1 minus this probability, and that would tell us the probability. So that's how you could use z-scores. You would need a z-score chart in order to do that, but these were standard in like textbooks so that students could look up and figure out what the probability would be for that. Here's what we now can do instead of that. So what I'm going to do is, instead of using the z-score, which is dependent on you having a z-score table handy, I am going to use what's called the normal CDF command on the calculator. This is cumulative distribution function. We're looking at a range of values. So here is where it is. So you're going to go on a calculator page, menu, statistics, distributions, normal CDF. Now notice what we have here, the lower bound, the upper bound. This is the Greek letter mu. Greek letter mu is another letter used for population, for mean. There's really two different types of mean or averages. There's sample mean, which is X bar, and population mean, which is mu. If you take AP stats in a couple years, you'll learn much more about that. For this, just assume that the mean given these problems is mu, and then the standard deviation. So what are we looking at here in this problem? I want to know the probability that this value is greater than, we can use greater than or equal to, that doesn't matter, 1075. So when I fill in my values here, my lower bound is 1075. My upper bound, it goes up forever to infinity. So your infinity symbol is right here. If I press pi, there's infinity. Our mean was 1,000, and our standard deviation was 50. And fill that in. And there it tells me the probability is 0.0668. So 0.0668, which is 6.68% of the data, which looks like what it fits in that range that we thought it would. All right, what's the probability that the light bulb will last between 860 and 970 hours? So this is really just asking what's the probability that it is between 860 and 970. So I can use the same command. Menu, statistics, distributions, normal distribution, normal CDF. This time our lower bound is 860. Our upper bound is 970. We have that the mean is still 1,000. And the standard deviation is 50. And we get that 0.2717. 0.2717. So 27.17% of the time. And if I look here, 860 would be about here, 970 would be here. So that represents about 27.17% of the data. So this is how this is used. It is used when those values that they're asking aren't conveniently just 1 or 2 or 3 standard deviations from the mean. And this allows you to figure out the probability that those events will occur. So what I'd like you to do is try 2A and B. Leave part C, but try 2A and B and see how you do. And I'll come back on and go through it here in just a moment. All right, let's take a look at this. The speed of vehicles along a stretch of highway varies according to a distribution that approximates a normal distribution with a mean of 56 miles per hour and a standard deviation of 6. The current speed limit is 65 miles per hour. What proportion of vehicles who obey the speed limit? So, what's the probability that their speed is less than or equal to 65? So, we've got menu, statistics, distributions, normal CDF. In this case, we are going from negative infinity. Our maximum is 65. Our mu, or our average, is 56. And the standard deviation is 6. You could draw a bell curve and kind of see where this would fit in, what you could give a guess. What you would see is that this comes out to be 0.9332. So 0.9332, or 93.32% of the cars. B, a new rule indicates that vehicles that are too slow will also be given a traffic ticket. The standard minimum speed limit for such a highway is 45 miles per hour. Determine the proportion of vehicles who will go slower than the minimum speed limit. Draw a curve and shade the area. So this is kind of what I was saying in the previous problem. We can kind of get an idea of what our answer is going to be by, and then the calculator can kind of verify that. So we have in this one 56, 50, 44, and 38. And going this way, 62, 68, 74. So the question is, how many are going 45 miles per hour or less? Well, again, we know at 44, that's 2.5%. So it's somewhere between 2.5 and 16%. So the question is, what's the probability that it is less than 45? And let's see if our hypothesis is correct based on what we're seeing here. So we have for this, statistics, distributions, normal CDF, Lower bound is negative infinity. We're going to 45. The mu, or the average, is 56. The standard deviation is 6. And let's see, our guess should be, yep, so 0.03337. So 0.03337, or 334 if we want to round. So 3.34% of the cars would be getting a ticket for going below the minimum speed limit. Now part C. A new speed limit will be initiated such that 13.5% of the vehicles will be over the speed limit. What is the new speed limit based on the criteria? So here is what we have. We have our curve. We have our bell curve that goes like this. We have our 3 standard deviations. We have the 56 in the middle, 62, 68, 74, 50, 44, 38. So the question is, we want to find a value so that this is the percent of cars that are exceeding the speed limit. Well, 13.57 means more, exceeding. That's got to be somewhere in here between 62 and 68. I'm going to call this X like asterisk. So somewhere in there, this area would be 13.57%, right? Because it's 62, up to 62, we have 84% of the data. So that means 16% of the data is greater than 62. So we want to figure out what this value is between 62 and 68 so that 13.57% of the data is above that. So what we're going to do is on the calculator, we are going to use the command. I don't know if you saw as we're going through other commands. There's a command there called inverse normal. So remember, we've done inverse operations this year. It kind of works backwards, right? We're trying to undo something. So what we want to know is what's the probability that these speeds go over that X asterisk that we're going to find. Now, when you're doing this, what we need to do in order to figure out that it's above, we've got to do, we've actually got, because when you do the normal, sorry, let me flip this up. When we do this, the value has to be, really what you're getting is less than. So we need to do 1 minus, oh, sorry, I don't know what that was, 1 minus the value that we were looking at, because this inverse normal is always going to give you the area smaller. So if I do inverse normal with this percentage, it's really giving me a value here on the left rather on the right. So if I do 1 minus that, I get 0.8643. So that 8643 means this 86.43% would be going at the speed limit or below. When we use inverse normal command, we've got to make sure this is less than. So to make that a less than, we do the 1 minus. And so now what we're going to do is we're going to figure out what is X asterisk. And here's how you do it. You go back to your command, menu, statistics, distributions, inverse normal. The area, that's the probability. And remember, that's always going to be less than. So the area we found that's less than our ideal value is 0.8643. The mean is 56. The standard deviation is 6. So it's going to work it backward for us and come up with the value that they should set the speed limit at is 62.599 miles per hour, which makes sense. It's right between that range of values that we talked about. So inverse normal is used when you're given the percentile and you've got to work backwards to find a value on the curve. So those are situations where you're going to use the calculator with normal distribution. Good luck working with this. I think you'll see it's pretty easy as you go forward. And I will talk to you guys one more video later this year, but take care and I'll talk to you soon.